Can you see my screen, everyone?
Yeah, we can see it.
Okay, that's perfect. The presentation is Analytical Breeding Tools, FielDHub, and MrBean Part 1. For this session, we have the topics. The session 1, we are going to discuss FielDHub and MrBean. And we are going to review the importance of design of experiments in research and development. We are going to review as well the key concept of DOE, as well the common experimental design we use in agriculture and plant breeding. We are going to review the concepts of spatial correlation in field trials, and we are going to show how to create experimental designs using the FielDHub app. For MrBean, we are going to talking about modeling single trials, linear mixed models, heritability, concept of blobs, and model comparisons, CRD, RCVD, alpha roll call, and spatial approach. As well as we are going to do a demo of MrBean of how to analyze the data from field for our experiments. At the end, we are going to have some conclusions and questions. For the next webinar that is planning for March 9th, we are going to approach. That's fine? Okay.
March 10.
It's March 10.
It's Friday,
okay.
March 10.
Okay. Yeah, March 10. We are going to approach other type of experimental designs. For today, we are going to talk about the replicated designs, but for the next session, we are going to talking about unreplicated designs, P-reps, augmented row column designs, as well as we are going to talk about a new feature that we put in FielDHub that is sparse testing or sparse allocation for multi-environment trials. As well as in P-reps, we can do something that is called average allocation in partial replicated designs for MET trials. For MrBean, we are going to talk about as well the MET trial analysis, MET trial analysis, two-stage, G/E interaction, factor analytics models, and GBLAB using the R package summer. Some conclusioning and question for the next as well. What is FielDHub? FielDHub is a design of experimental application that aids in the creation of traditional and replicated, augmented, and partial replicated designs applied to agriculture, plant breeding, forestry, animal, and biological science. And all the people that I contributed to FielDHub, Dr. Salvador Guesan, Johan, Ana Maria, Richard, and Matthew, that is in here. That is as well a collaboration between NDSU and the CIAT. I want to introduce you FielDHub, but before I would like to mention some of the most common experimental design use that we use in plant breeding and agriculture and their strengths and weaknesses. I will also discuss the importance of randomization, replication, and blocking in experimental design and how these steps can improve the validity and reliability of your results. For that reason, the importance of DOE in research and development. DOE is very important. For example, proper experimental designs is essential for obtaining reliable experimental results. These, if we make good experimental designs, for example, in plant breeding and agriculture, we can find or we can ensure that the selection process is based on the actual performance of the plants rather than on random, on extraneous factors, as well as we can improve crop yields, enhance the overall quality of crops, develop crops more resistant to disease and or environmental stressors, as well as we can select the best performance plants for the further breeding and commercial productions. I want to mention 3 key concepts that we have in experimental designs. The first one is randomization. Basically, randomization is the process of randomly assigned treatments to experimental units to control for extraneous source of variation and increase the experiment's validity. Randomization helps to ensure that the results are reliable and valid. It reduces the risk of bias and helps to increase the results' precision and accuracy. The other pretty important concept is replication. Basically, replication means repeating an experiment multiple times to reduce the effect of random variation and increase the precision of the results. As well, blocking. We usually do blocking. Blocking means grouping the experimental unit in homogeneous blocks to control of extraneous source of variation and increase the experimental validity. The important in here, the importance of blocking is that we can help to control for source of variation related to the blocking factor or lending to more reliable results. In here, I want to show like 3 concepts with a toy example: randomization, replication, and blocking. Let's say we have 2 treatments. One, we can say uncontrolled, and one treatment T, control C and the treatment C. And we want to allocate that in 4 replications. And for example, let's say we have this field. In this way, like the right way for allocate the blocks. As well, where we can see that the C and the T are randomized. They are not in the same position in the blocks. We are applying randomization, blocking, and also the best way for allocate the blocks. The other concept that I want to show in here is if you know like the blocking factors, for example, in here, the type of soil, we should like allocate the blocks depending on the blocking factor. For example, in here, depending on the type of soil. Usually, experiments in the field, we have spatial correlations. But what is a spatial correlation? Spatial correlation means that when experimental units are close to each other, for example, we are talking about plant breeding on agriculture, that it plants, when the plants are close to each other, they often have similar results. If you have 2 plants next to each other, it's usual that the performance of each plant is pretty similar. Yeah, this happened why in field trial, spatial correlation can arise due to variation in soil, sunlight, moisture, temperature, management effects, and other environmental factors. Spatial correlation can impact the validity and reliability of experimental results. Researchers can use spatial correlation techniques to address spatial correlation, such as these techniques can be splines and autoregressive models. There are others, but just I want to mention this for today. And the good part is by accounting for the spatial correlation, researchers can improve the precision and accuracy of the estimates and draw more accurate and reliable conclusion about the effects of the treatments on the response variable. Usually, experimental designs can change depending on the research question and the nature of the experimental units. Additionally, different designs have different strengths and weaknesses. Choosing an appropriate design requires carefully consideration of the sources of variation that need to be controlled and the specific research question at hand. For this, let's start with the basic experimental design, that is the complete randomized design CRD. This is the simplest and most basic experimental design where all the treatments are randomly assigned to experimental units. It is appropriate when no extraneous source of variation can affect the response variable. The strength is of this design, it is simple and easy to implement, while the weaknesses is the lack of control over its extraneous source of variation. For example, for this, let's say we have 12 treatments. It can be any kind of treatment, and we want 4 replication for each one. As you can see, this layout, I generated this layout using FielDHub. You can see we have treatment from T1 to T12, and they are randomized to the field. For example, we can say this is a field on arrangement in a greenhouse, and each treatment has 4 copies of 4 replications. Maybe the most common or most known experimental design is the randomized complete block design, or RCBD. This design is useful when the experimental units can be grouped into homogeneous blocks and the treatments are randomly assigned with each block. It is appropriate when extraneous source of variation can be controlled by blocking. The strength of this design is the ability to control for extraneous source of variation. The weakness is its limitation to, or the ability to test a large number of treatments. We do not recommend like I use this kind of treatment, this kind of design when you have a large amount of treatments that you want to test. Yeah, what's happened if you have a large amount of treatments, you want to allocate the treatments into the blocks, right? But we have the assumption that those blocks should be homogeneous. But if you have many treatments, that is pretty possible that is no longer homogeneous. Yeah. For this example, we have 18 treatments, and each treatment is going to appear we have 3 times. That means we have 3 replications. There is another kind of experimental designs that we use a lot in agriculture and plant breeding, that is the incomplete block design. Sometimes it's not possible to allocate all treatments to complete blocks in an experiment, right? This can happen for a variety of reasons, including limited resources, physical constraints, or a large number of treatments. For this specific experimental design, we have like an incomplete block design of size V, K, and R is an arrangement of V treatments set up from an incomplete block of size K. In this case, in an IBD, randomly assigned treatments within each incomplete block, but not every treatment is applied to every block. That is like the main difference with the RCBD. In the RCBD, all the treatments are in the all blocks. In this case, not all the treatments are in the incomplete blocks. They can be more efficient than the RCBD when the number of treatments is large. For this particular example, we'd say we have a number of treatments B of 15. The size of the incomplete block is 3, and we want 3 replication for each treatment. As you can see in here, in this part, we have the first replication. The first incomplete block contains the treatment 13, the treatment A, and the treatment 10, and so on. Alpha lattice design, there are kind of type of incomplete block designs. Researchers can use lattice designs such as balanced incomplete block designs and partial balanced incomplete blocks design when comparing a large number of varieties in agriculture experiments. The first type of lattice design is the square lattice. In this particular type of design, the number of treatments should be a perfect square number, and the block size is the square root of this number. For example, if you have a number of treatments equal to 100, that you can use a square lattice to randomize your experiment, and the size of the incomplete blocks should be the root square of the those numbers. The number of the replications are flexible. You can set for 2, 3, or 4, depending on the needs of the research questions. The second one is the rectangular lattice. In this case, the number of treatments V is equal to the size of the incomplete block multiplied for the size for the incomplete block plus 1. These treatments, this total amount of treatments, so this design has incomplete blocks of size K. The same notation, V, K, and R, but I really like this design because it is like a complement of the square lattice. For example, if your number of treatment is not a square lattice, you still maybe can use a rectangular lattice. But if the number of treatment is not a square number, also you cannot use a rectangular lattice. There is another type that is more flexible, that is the alpha lattice. This design is one of the most flexible experimental design in plant breeding agriculture. It is also known as a generalized lattice. This design is useful when we have a large number of treatments, such as cultivars or genotypes. For example, in this case, we can say the number of treatments equal to 80, and we can set the size of the incomplete blocks equal to 5, and maybe we can set for 3 replications. Just I want to show you one example for each one. Let's say we have a square lattice of size, so with 64 treatments, the size of the incomplete blocks is the square root of this number, and we want 3 replications. You can see replication 1. You can see that the incomplete blocks are in the columns. Each part, for example, this is the first incomplete block. Sorry. This is the first incomplete block, the second incomplete block, and so on. That is for this type of design. Let's say to the rectangular lattice. In this case, for this particular example, we have 56 treatments that you can set up like the treatments is equal 7 multiplied by 8 equal to 56. The size of incomplete blocks for this case is 7, and we have 3 replications. And the alpha lattice, for example, in this case, 80 treatments. The size of the incomplete blocks are 5, and also we have 16 incomplete blocks to complete the entire 80 treatments, right? Now that we review the key concepts of the experimental design, we can move into the demonstration how to create these type of experimentals using the FielDHub applications. Let's see. Let's share my R. Can you see RStudio?
Yes.
Yeah, we can.
Okay, yeah, the first step for using FielDHub, you need to have R and RStudio installed in your computers, and install from, you can say, for example, install from CRAN, and you can say install that packages and FielDHub. Sorry. And hit enter. I won't do that because I already have the package installed. And after that, everything installed in your computer. The only thing that you need to do is library, FielDHub. And you can say, for example, FielDHub and : and run application. After that, it's going to open a new tab in your preferred browser. Can you see the application now running in the
Yes.
browser? Okay, that's perfect. This is the application. We have a lot of menus in here, but that is, I don't want to talk too much about this today, but we have unreplicated designs, partial replicated designs. We have the lattice designs, and also we have other designs, so we can call as well, like the classic ones. In this tab, we have the complete randomized design, the CRD, the randomized complete block design, Latin square, factorial design, split plot, split plot, strip plot, incomplete block design, and a resolvable row column design. Let's start for the basic one. That is the complete randomized design. After you select the option, they're going to display some options or parameters to set the experimental design. The first question that I'm going to do to you, ask to you, the application is, do you want to import the list of treatments or the entries for make the randomization? If you already have that, for example, in a CSV format and Excel, you can say yes. And the only thing is that you have to follow this format to upload the treatments. You need to upload, for example, a CSV file with a single column with the name of the treatment, and FielDHub is going to care about the randomization. Yeah, but for this time, just I want to set to 12 treatments. I want 4 replications for each. You can set like the layout for the randomization, for the plot. You can set the plot number. You can set the name of the site or location or the greenhouse where you are going to make make the experiment. And also you can set a seed number. The seed number is pretty important because it's like eventually you want to do the same randomization for these specific parameters, you need to use the same number. Yeah, let's do it. After that, they generate for you the randomization. As you can see, we have treatment from T1 to T12 because we have 12. And also you can choose maybe 2 options in here, like for verify the randomization and like for the layout of this experiment. You can see, for example, the plots as well, 101, like the plot number. And in here, after that, you have like the thing that we call field book. In this field book, we have an ID for each row, the name of the location. We have the plot number. We have the row and column. If you want to use this information, this row and column is based in the layout that you generated in here. And also we have the replication and the name of the treatment. Yeah. If you are teaching statistics, you can use this application as well for showing, for example, how to make an ANOVA. You can generate some information in here. For example, you want to generate for values for yield, moisture, height, and other variable if you want. Let's do it for the year. We'd say from 34 to 60. And after that, you can go and automatically the application is going to generate a new column for you with the values of the simulated data. Yeah, usually I know people that use this application for teaching as well. They generate some data and then go and show how to make an ANOVA with this information. Also, they show how works the randomization process. The other type of design that I want to show you today is the randomized complete block design. The first you need to select if you want to upload the list with the treatments. And if not, just put in here the number of treatments that you want to randomize, then the number of treatments that you want to replicate the experiment, and the number of locations. This application allows you to make randomization across multiple locations. Let's set just for one today. Also, you can set Serpentine or Cartesian for the plot layout, and you can plot the number, for example, 1000 for this time, the name of the location, and the seed number, let's see 2. And you can run the randomization. As you can see, we have 3 blocks. Each block contains 18 treatments. but the randomization in each block is different. I forgot to mention something about the blocking. Blocking is just a restriction to the randomization. Yeah, the randomization. We do the randomization separately for each block. In here as well, you can visualize the randomization or the layout in different way. Let's do it in this way. That is, or in here that you can see different ways to also you can put like a block side by side if you want. And also you can see the plot numbers. If you generate some data, let's do it, for example, from 60 to 120. You can see, for example, a heat map of the simulated data. And if you go to the field book, now you have the ID, location, plot, row, column, replication, the treatment, and a simulation of yield along with the randomization. Also, you can save this information, any design you can save into your computer and open in Excel or import to the database if you have a system database in you. The next one that I want to mention is the incomplete block design for today. That just I mentioned in the presentation, this is like a variation of the RCBD where not all the treatments are in all blocks. Let's say we have 15 treatments, 3 reps only. And now you can set automatically based on your parameters, you can say the number of or the size of the incomplete blocks. That means how many units or how many treatments you want to put in each incomplete blocks. Let's say I want 5 maybe, and 1 location. Let's do this in number 45 and run. And now we have the randomization for incomplete block. This is the first block or replication, and this replication has 3 incomplete blocks or internal blocks that some people call it. In the first internal block or incomplete block, we have the treatment 13, 14, 8, 4, and 11, and so on for the others. You can maybe see other ways to visualize this. For example, in this way, each incomplete block is in this row, in each row. Also, you can see the plot number depending of it is serpentine or Cartesian. Let's do it the lattice designs. We can start with the square lattice. Let's do it, for example. Okay, if you have a square number in here or a perfect number in here, automatically they are going to show in here like just one option for the size of the incomplete block. And for example, if I put 50, they are going to say, okay, we don't have option for this because 50 is not a perfect number, right? But if I keep, for example, 64, automatically they'll show you, okay, 64, we can do it. And let's see that I want only 2 replications and 1 location. Let's say that I want 2 locations. And the first location is going to be Fargo, and the second location is going to be Castleton. And run the randomization. Okay, we got it, the square lattice design for the first location. This is the first location with these parameters. If you want to see the second location, you can choose the location view from here. And now if you can see, the randomization should be different. We have 14 in here, but for the second location, you have 10. Yeah. Each incomplete block is in this way. Each incomplete block is size 8. And also you can visualize this in the other way, side by side, if you want.
And Didier, can you show them how can they extract the map utilizing
Yeah, absolutely.
the Excel?
Yeah. If you click here, Excel, you can download your map of the randomization. Let's do it in here, downloads. Okay. No. This is like the layout. This is the columns. This is the, we have like the row 1, 2, 3, 4, 5, 2. Okay, yeah, this is the location 2. We have, this is the column 1, column 2, column 3, and this is the randomization. This is like you can use this like as a map for your field if you want. Also, you can download this image. You can open in here, you can print it. Values. And let me show you just a heat map for this data that I simulated. And now you have a field book with the randomization and a response variable with data, with synthetic data for yield. The same way for rectangular lattice. Rectangular lattice is more restrictive, but it's a complement for this for the square lattice. Let's say that if you set up 31, let's say, okay, this is not a setup for a rectangular lattice. Let's do it 56. And now we have the size of the treatment, and you can generate this. You can visualize in different ways. If you want, you can see the plots, how it's going on with the plots numbers. And if you want simulate, you cannot see it because you need to simulate some data to make like a heat map before. As well, you can download this field book to your computer. And the last one is the alpha lattice. This is the most flexible design for agriculture. You can say, for example, 80 treatments. I want to, after that, you set up the number of treatments, you set up the replication, you can set up the size of the incomplete blocks. For this case, you have a lot of options. You can say less is better, like smaller incomplete blocks are better than bigger incomplete blocks. Yeah, let's say 5 and run it. As you can see, this is the setup for the experiment, and you can change it at any time. Yeah, for example, let's see the 2, let's see the 4 one. I don't like this too much, maybe this. Yep. There is also, if you want, you can set up in the side by side. This is always up to the researchers how to like deploy the experiment to the field. Also, you can see the plot numbers. This is a serpentine 101, 102, 3, 4, 5, and finish here and come back from here. This is like the serpentine layout. But if you want to finish in here and start in here, you can set this option or this parameter as Cartesian if you want. Let me show you something about us. We have, as you know, I'm Didier. We work in this also with Dr. Salvador Guesan, Dr. Ana Maria Hellman, Matthew Siffel, Johanna Paricio, and Dr. Richard Horsley. As well, if you want more information about, we have, you can view this on CRAN. This is an R package you can download at any time. We have like the manual for all the thing that I did in the application. Also, you can do it in the console using the native functions that FielDHub has for making the randomizations. As well as we have a a publication of the application that you can mention if you want, if you at some point using this app, and if you want to mention that is you use FielDHub as well. And the other part that I want to use is we are running a YouTube channel where we usually put some tutorials on how to use FielDHub and how to use MrBean for FielDHub for making randomization, creative experimental design, and MrBean for making the analysis. As well as we have the GitHub that is public, and where you can enter, you can review the code if you want, and you can download. It's totally free. And we currently have 8,519 downloads from Arcan. And you can download the package with this code, or you can download like the dev version from GitHub from here. If you have more information about the package, you can go here and see like the tutorials. We have articles for each function. For example, let's go to the square lattice. You have like a tutorial how to do a square lattice using the application FielDHub, as well as using the code in R. You can plot the designs using R as well. I think that is my side. If you have questions, if you have no ideas for FielDHub, just let us know. And yep, thank you so much for having me.
Thank you, Didier. And yeah, so the second part of this presentation, then we will have Johan Aparicio. So Johan, please go ahead. And
Okay,
I don't
perfect.
know if you want to have any
was-
Q&A at the end,
Yeah, I was
Kevin.
about to ask you if there is questions, because probably we can answer first and then move to the second part. I don't know how to proceed.
Yeah, if there are
At the
no
end?
questions, we can do it at the end altogether. Yeah, go ahead, Johan.
Okay, perfect. I'm gonna share my screen. Just give me 1 second. Thank you everyone for joining us. I see a lot of people here, so which is quite nice. Just let me know when you can see my screen. Perfect. Can you see my screen?
Yeah, perfectly.
Yes.
Yeah, we can.
Okay. So this is MrBean. As Ana Maria mentioned before, this is an easy to use Archini package that try to make the analysis of field trials easier and accessible for everyone working in plant breeding, especially, And this is a collaboration with NDSU, or also Salvador has been supporting the development of this product. Didier is here, Ana Maria is also here, and some other colleagues from the Alliance Biodiversity International and CIET. So just to start, Didier mentioned something about this, and it's basically a common field scenario that breeders face, etc., which is basically that the experimental field is never completely homogeneous. That's something that we know. That even before the plants are established in the field, there is some level of variability, etc., etc. And in addition to that, we can face variation because of management effect, also fertilizer or irrigation, etc. In all of these components, as Didier mentioned, can cause, a spatial correlation. That means that experimental units that are closer together tend to be more similar than the plots that are separated by greater distances. So, which is basically the concept of spatial correlation. I want to make emphasis in this row and column information in the experimental designs, because we saw during the previous presentation yeah, that all the experiments, I mean, that we were able to plot the experimental design, but we didn't mention in pretty much detail the row and column information in the experimental design. I mean, even though we have, for example, randomized an experiment in RCBD or CRD, alpha lattice, et cetera, we are able to add 2 additional columns to the randomization, which is basically this layout that Didier was showing us previously. So I'm here just different like figures just to explain a little bit about the concept. Just let's think for a minute about the experimental unit. This is just a bean plant. I have several plants in the plot. And let's assume that this is my experimental unit. And as Didier was basically presenting, if we assume that this is an RCBD, we have 2 blocks, right? And let's assume that we have 9 genotypes or treatments. So we have the concept of randomized complete block designs, but it's just to add 2 additional columns, let's say, to the randomization, because we can think about a Cartesian plane is something like that, XY axis. This is the row information, this is the column information, and each individual unit or experimental unit is gonna have a unique row and column information. So for instance, this one has the column 1 and the row 1. So each individual unit is gonna be identified by row and column information. This is, for example, the column 6 and in the row number 3. So this is just an example, but now in the real life, this is our field. This was a picture taken last year. And just to illustrate again with the real picture, we have the column, we have the row, and just let's assume that this is my block 1, this is the rep number 1, this is my rep number 2, and each of these plots are basically my experimental units. Each plot is a unique genotype in this rep, and it has a copy in the second block. What we try, I mean, when it comes to field trials, I mean, what we try is basically to separate the different sources of variation. We have here the raw data. Now it's easy to understand this plot because we already know what row and column mean. So basically, this is showing us the response variable, you know, using the row and column information. And here we can see the colors. Yellow is because we got higher yield, and blue ones is because we got lower values for this response variable. In this case, it sets raw data, but it's the yield response variable. What we try is to separate, you know, what is genotypic, what is spatial variation, and try to reduce as much as we can the residual variation. So there are different models depending on the randomization we carry out. I mean, we will have an equation basically to run an analysis. So Didier mentioned the completely randomized design, randomized complete block design, alpha lattice, row call. In analysis, I mean, when it comes to analyze the data, we can combine them, you know, I mean, to use the row and column information, but also use the incomplete block. And also we can use several approaches to model the spatial variability. As Didier mentioned, the 2-dimensional splines, the P splines, can help us to model the spatial variation. There are several approaches. One of them, which is also very famous, which is the autoregressive correlation between rows and between column, which is available in ASREML. But you know, there are several approaches to take into account the spatial variability. I have to say that they are not experimental design. It's just a different way to analyze the information. Because as I mentioned before, if I have a randomized complete block design, but I have also saved the row and column position, I will be able to analyze the data set as a row column because I have the row and column information. I have to make emphasis in linear mixed models because this is basically the engine we use to analyze the information. So mixed model extends the linear model, the traditional analysis of variance, by allowing a more flexible specification of the errors and other random factors. So it allows for a different type of inference and allows to incorporate correlation and heterogeneous variances between observations. So in the classical ANOVA, we only have fixed effects. In the mixed model approach, we have random effects. So fixed effects are those factors whose levels are selected by a non-random process, and random effects are factors where its level consists of a random sample of level from a population of possible levels. And mixed linear models contain, well, as I said, both random and fixed effects. And there are different, this is a very common question. How do I consider this factor? I have to take it as a fixed, I have to take it as random, but we can find different ways, different questions that we can try to answer just to make sure that we are taking the factor in a proper manner, in a correct manner. So how many levels of the factor are in the model? Would the same levels be used again if the experiment were to be repeated a second time? Are the level of a factor determined in a non-random manner? Are inferences to be made about the levels not included in the experiment? Is the number of levels in the population is large enough to be considered infinite? So all of these questions can help us to, to make the decision of taking the factor as a fixed or random. You can find more information here in this link if you want. And this is a very critical parameter in plan breeding, because this can also help us to, I'm thinking about comparing different models. So this parameter can be used as a criteria to compare different models. And I'm just including this because I wanted to make sure that we have this clear. This can be defined as the proportion of phenotypic variation that can be attributed to genetic differences. So the phenotypic variance can be divided between genetic variance and can be divided to genetic variance and error variance. And that proportion of phenotypic variation that can be attributed to genetic difference is what we call heritability. So the most common equation is this one, Brosen's heritability, which takes the genotypic variation in on the numerator and then the phenotypic variation on the denominator. There are several ways. In literature, we can find several methods to estimate the heritability. The standard heritability, the one that I showed you before, the college heritability, regression, the blue and the blob, Aoki et al. In 2006. PIFO also has a way to estimate heritability. But the one that we have been using most is basically the college heritability. It has some particular things, very like it consider many other things that the other ones probably not. So that's why we have been using this one, and this college heritability is the one that is implemented in MrBean. So if you are wondering what is the heritability that we are gonna see on the tool, is basically college heritability. Here I leave a paper. You can find more information about estimated Brosen's heritability. About the calculation. So as I said, this is a proportion of phenotypic variation that can be attributed to genetic differences. Just to measure, if I were to calculate this, what do I need? I need, for example, it's just, as Didier mentioned, experimental design, that was something that we need. Replication, I mean, the key concept of the experimental designs, that's what we need. And an engine to estimate the variance components. In this case, linear mixed model to estimate the genotypic variance, to estimate the residual variance. This plot basically tried to present this in a different way. Just phenotypic is what we see, you know, the raw data, genotypic value, environment, and error is the rest. There is a connection between the editability and the blobs when it comes to selecting, you know, new genotypes. So we tend to use blobs. But why blobs? It's because this is a method of estimation for genetic effects, which is in a sense try to anticipate the shrinkage towards the mean observed in the progeny. So instead of waiting for a disappointing outcome in the next season, blobs compute a shrunken estimate of the genetic effects in the current season. And I mean, if we compare blues with blobs, we will see that the genotype with largest least square mean will be shrunk downwards, while the genotype with the small least square means will be shrunk upwards. So what is, the degree of shrinkage is exactly that, the editability, what we have been basically talking, because it depends on both the genetic and environmental variation as assessed by variance components, which is the editability. I have here just an example of that. I have 378 individuals, and I have the estimation of the blues and the blobs here. We can see that this has a higher range, while this one has a lower range. The variation tends to go to the mean. This is basically the shrinkage, and that level of shrinkage is what is called the editability. This is also a method for estimating the broad sense editability. We fit a linear regression, and we take the slope of that linear regression, and that's going to be the editability, the broad sense editability. Let me check. Here I have a motivational example. Let me check. This data set was carried out in Darien 2016. I really like this example because I don't know why, but you will see in a minute why, what is the reason why I really like it. But I have in this one 380 genotypes in 2 reps, and it was randomized as a alpha lattice design. So this is how it looks like. This is basically the randomization. This is an alpha lattice, 2 reps. You can see here these dashed lines. That means that this is an incomplete block. And in total, I have 1, 2, 3. Yeah. We have around 17 blocks, around more or less. And in each of the reps. And with this example, what I want to do is just basically omit information. This is an alpha lattice design. I have also the row 1 column information in the field, so I'm able to create the field map. This is basically what we are seeing here. And I'm gonna just assume that I don't have the row column information, that I don't have the incomplete block, that I don't have the rep, etc., just to see what is happening behind, What if I omit the rep? What if I omit the incomplete block? What if I add the row and column information? Just to see what are some of the advantages of considering all of this information. So there are different criteria to compare AIC, BICs, pseudo R-square can be used. The readability, as I mentioned before, can be also used to compare, you know. If we are able to reduce the error, probably we are going to be able to increase the readability for that trade, etc. And also we can use the residual variance because, you know, in all these models, we try to reduce the residual variance, I mean, to have a less error, let's say. And in that way, for example, we are able to compare different models and see which one is or can be better, for example. I have here the criteria, the standard, the error, the genotypic variance, the irritability, and the R-square. On the x-axis, I have, you know, CRD, RCVD, alpha, roll call with an alpha component in SPATS, which is basically the two-dimensional splines for modeling the spatial variation. What I have here as a CRD is basically, you know, the same data set, but just omitting the rest of information. Just, okay, let's take the mean, just analyze this, omitting the rest of information about the experimental design, and just see what happens with, I mean, what happens to the error, what happens to the genotypic variance, etc., etc. So this is what we have here. CRD, for example, is this one. That's what is happening to the error, is the one, is the one with the highest error. I mean, omitting all the information. The ones with the lowest genotypic variance is the one with the lowest irritability and also with the lowest R-square. And we can see here the values. You know, CRD is the worst one in this case. And let's take a look at the more advanced or sophisticated, which is the one that contains the two-dimensional splines. We can see here the error. This one is the one with the lowest error. It was the one with the highest genotypic variance, highest row sense irritability, and R-square is also the highest. We can see here in pretty much more detail the values of the error variance, the genotypic variance, and the irritability. When we omit everything, we got 0.42, but when we add all the information, we end up with 0.64 for the Brown sense irritability. This is an R-square, just comparing somehow the percentage of variance explained by the model, and we can see that it does something. Now, you know, most people don't believe on this criteria. I don't know, but my point is that using a different approach to show that I don't know, that something can be better is using plots, you know, something graphically. Here we have the completely randomized design, but you know, we have the row and column information, so we are able to plot the raw data, the fitted data, which is basically, yeah, as his name says, the fitted data for the model. The residuals is comparing the raw data with the fitted data. It's just the difference. Effects, I mean, we don't have anything else in the equation, so we are not gonna see something here because we only have the mean, and we have the genotypic factor and error. So here we have the genotypic blobs residual, and this is just an histogram of the genotypic blobs. Look at this. The raw data and the fitted data, they don't look very similar, you know, and that's why the residuals are basically reflecting what we have in the raw data. So that means that we are not modeling many sources of variation, and the residuals are not independent, because what I see here is a clearly pattern, you know. In the middle, we have higher values, and in the borders, we got lower values. That means that there is a spatial variation, and I mean, there are many other sources that we are not considering. As I said before, the yellow ones are the highest values, and the blue ones are the lower ones. They were lower ones. The same happened to all of these. What if we consider the block? You know, now okay, let's assume that I'm gonna add the block into my model. So here we can see that almost nothing happens, because as Didier mentioned, an RCBD for this amount of genotypes, I mean, it's not gonna do anything basically, because it contains like almost 400 individuals, so it's a big block. So it's not gonna do anything basically. What if we basically model the trial as it was randomized, which is an alpha design? We can see here the incomplete blocks. They are doing something quite good. They are modeling the spatial variation. Now our fitted data looks very similar to the raw data, and now the residuals have changed a little bit. Now there is not that strong pattern in the residuals. They are cleaner, let's say, than compared with these ones. Now, what if we add the row and column information? So we can see here more pixels. And when I see this plot, it's kind of like to have a camera, you know, I am increasing basically the number of pixels for my camera. It's just, I mean, like the resolution. And this is the effects of the design. Now, what if I include also the incomplete block? So I have the row, the column information, and also I add the incomplete block. So now I can see here, it is doing a good job. I can see the residuals are, I mean, they don't have a pattern. That's something quite good, you know, that's something that we are looking for. And using the spatial approach, which is the one that has these two-dimensional splines, what we see here is like a smooth, you know, and as I mentioned before, I mean, the number of pixels, 2 pixels, 36, etc., and we are basically increasing the number of pixels, and we have basically a better resolution for this. Our fitted data is very similar to our raw data. That's why we saw that R square pretty high when we include the row and column information. And yeah, this is basically a GIF illustrating all the changes. So, well, some of the tools and packages available for running linear mixed models, probably you have heard about some of them. SPATS, spatial analysis using splines, Rodriguez et al. In 2018. ASRMLR, LME4 for feeding linear mixed effects models, and Sommer also. And all of them have been integrated into MrBean. So you are gonna be able to run SPATS models using this engine, this approach. ASRML also, LME4, and also Sommer for something specifically. What can MrBean do for you? So it has a panel for importing information. You can also get data from read-based or BMS. It has also a module to do a descriptive analysis, scatter plot, box plot, distribution, mean, variance, CB, etc., etc. The model that contains the SPATS approach. So you are gonna be able to run these models, estimate the blobs, blues, heritability. Also, something that I didn't mention, it was the outliers, which is pretty important when it comes to data analysis to check if there is something strange in the data. spatial trend, variance components, etc. Also, we have a module to estimate or to run multiple side by side, multiple trades, also using the SPATS approach, and also single side analysis using the ASRML package. Now the approach changed a little bit, but we end up in very similar results. We have also a model selector for ASRML, because in ASRML it's kind of difficult to find the best model. So there is a model selector for ASRML models. And the MET analysis that we are gonna discuss next week which is using basically ASRML and also a two-stage approach. We are able to estimate or to feed factor analytic models on a structure, core GH, run principal components analysis, etc., etc. And the traditional designs using LME4, RCVD, CRD, alpha lattice, resolvable and non-resolvable row column, and also to estimate blobs plus editability and to identify some potential stream observations. In summer will help us to feed the G-blob analysis, estimate marker effects, genomic editability, variance components. But when this is when we have genotypic information or marker data. If we don't have, so we are gonna use the rest of the models. So let's jump to the demo. Let me check. Escape here. I'm gonna open R. But first I'm gonna show you. Oh, let me check that. I'm gonna use this. I'm gonna open a new browser just to show you how to find MrBean on GitHub. This one, perfect. And this is the repository of the app. You can see all the source code here. This R folder I have here. And the way we can install the app is basically copying this code that is in here. And once we copy this and run, and once it's basically installed, we need to run just a library MrBean and then run app. And then it will open in our browser. Yeah, here we can see basically the interface. This is how MrBean looks like. And yeah, basically this is the home menu. We have on the left side all the modules, the one for importing data, the one for running SPATS models, the one for running ASRML models, the one for running MET analysis, the one for running the G-blob, the one for running the traditional designs. So just let's go to this one. Here we have preloaded a data set just for you to be able to run something, I mean, it's just a Mickey Mouse data set to play with. But also you can import your own data here. You can import CSV file, TXT file, Excel files, etc. And also, I mean, here at CIAT, we use BMS. I mean, it's the place basically where we storage our information. So we use this also to connect to BMS. I mean, if you also have information in BMS, the only thing that you have to put here is the server. Here is our server is here. You have to use your credentials here. I have to say that we are also able to get data from Breedbase, if is that the case. And internally, we are using a beautiful package called QBMS. But yeah, we can talk about that later. Crops, we have here beans. We have to select the program. I'm gonna select this one, CIAT Uganda ashwagandha beans. And I don't know, just as an example, let's take this one. And I'm gonna, select this trial. I have the information here, so I can basically analyze the information without downloading and importing information like that. And I'm gonna just use this example I have here, which is basically the one that I presented before in the slides. And I'm gonna go through all the modules. So once we have the data here, we are able to plot the data. So the first thing that I usually do is basically to plot the layout, the randomization, just to check the randomization. If we have the row and column, we can see here, okay, the rep number 1 was located here and the rep number 2 here. We can see a color by, for example, block, because this was originally randomized as a alpha lattice. So we are gonna be able to see the blocks here. Here, the block number 1, here the block number 1 in this other rep. So in total, we have 18 blocks. Yeah. So we can do this, and also we can, we have the yield here. We are able to plot by column, for example, just to see if there is something in, or if this factor is affecting our variable. Here there is like a pattern, in the middle. We have the higher values in the middle and the lowest one in the borders. We can also plot by rep. For example, we can plot by incomplete block. Internally, we are using Plotly, so we are able to see it like in an interactive manner. And let me check by row, for example, when it comes to check the variation, the raw data. And it's interesting because in the middle, we see this pattern. Probably something happened to the borders, but in the middle, we got higher values, in this case for yield. We can basically select and play with these kind of things. We can also make zoom to the plot and also increase this just to have a better experience, and etc. Then we can jump to see the distribution of the variable, this is pretty normal. You can select here to see, let me check, something is happening. It's getting crazy. And we can estimate also, the mean, standard deviation, minimum, Q1, median, etc. Also by group. For example, I want to check by rep. Okay, this is the mean for rep 1, the mean for rep 2, the standard deviation, missing data if I have, etc. And also it's gonna be, this plot is gonna be colored by the factor you have here. So for example, rep, we can see by block, etc. We can see individual plots if we want. We have a lot of blocks, so they are gonna be plotted here. Let me check by rep. Yeah. Here we can see the variation for each of the reps. We can increase also here this plot, and also download. You will find this button through the different modules. So this means that we are able to download the plot as a PNG or a PDF. Once we are happy with the data, there is nothing strange, there is nothing wrong, we can jump to single site analysis. So here we can find a guide. It will guide us to the process of, selecting the response, the genotype, if we want to take the genotype as random or as fixed, the row and column information, if we want to add the rep, etc. If we want to add additional fixed factor, random factors, covariate probably, and then some buttons to just to run and to see some interesting statistics. And basically, we have here the yield. We already selected here, the genotype here. Then we got this output. This is basically, if you have used SPATs, I mean the R package, you might find this very familiar because it's basically the output that SPATs package gives you. Here we have the model plot. This is the same example that I showed you before. Raw data, fitted data, residuals, fitted genotype blocks, histogram, etc. And here we can see the spatial trend. The spatial trend, we can explore it in much more detail if we want. And also, I mean, we wanna see what is the editability or the variance components. For example, we can just press here, info box. This is the editability for this trait, the residual standard deviation, R square, and the coefficient of variation. You know, we are fitting the genotype as random, so what we expect is basically to get the blobs. Blobs here, predicted values and their standard errors for all of the genotypes. And, you know, we can jump to see the ranking plot, just a ranking plot. What is the best one, for example, here? Oh, this genotype is the best one with this yield. Which one is the lowest one? Is this one, for example. And you see that the standard error, it changes a little bit depending on the genotypes. I mean, this is because if we have more replicates, we are gonna have, let's say, a lower, you know, standard error, and in the other say around, the other way around. So this one, because it has probably missing values, so it's gonna have higher standard errors. Here is again the table with the predicted values and the standard error, and this is just the histogram of the predicted values. Something important is to check the residuals. They can cause a huge damage to your data when it comes to really strange data points. We will check an example just for you to know what are more or less the problems that we can face when we have extreme observations. Here, I mean, I'm just gonna jump to AceRemel just to show you what we saw previously. This is single site for AceRemel. I have here the yield, the genotype, the call and row information. I'm not gonna include the spatial correlation. I'm just gonna assume that they are independent, and I'm gonna fit the model. Just wait a minute. And then, you know, we can see basically the plots that we saw during the presentation. Raw data, fitted data, residuals. So we can see here the editability also 0.41. The diagnostic is just checking I mean, this is also an output that AceRemel give us. This is an input. Here you can see the equation we use to fit the model, the variance components, and a NOAA table for fixed effects, and some goodness of fit statistics for the model fitted. And here we can find a semi-variogram. It's also something that gives us AceRemel. What if, for example, I include the block as we were doing previously? What if I include the rep? So now we have here an effect here, you know. But as we discussed, this is I mean, our blocks have a lot of information inside, so it's quite difficult to use them just to model the strange variation. We can include the incomplete block, and we will be basically seeing all the results. Now this is the raw data. This is the factors related with the experimental design. We can see here the plot. Now is much better. And also we can start basically including different row and column, for example. Just, oh, this is the plot, etc., etc. And we are using basically ASRML for running the model. The approach that is basically the most common in ASRML is the autoregressive correlation. So I'm gonna remove this, I'm gonna remove this, and just I'm gonna use spatial correlation. So now I'm introducing these components into the residual. So I'm gonna introduce this autocorrelation between rows and between columns, this interaction. And as you can see here, the readability is quite good, and just by including those components, it does a pretty good job. But I can also include several, you know, I can play with splines. I can play also with factors, row and column. I can include the blocks, the incomplete blocks, etc., just to see which one gives me, I don't know, a better performance. But yeah, this is more or less. I'm gonna just import a data set to show you something related with the residuals. And yeah, this is basically the way we can, we can drag the file to these rows, but we can also search in here, you know. Once we import the data, we have to make sure that it was good read. Let me check, okay, row, column, etc. And yeah, let's jump to single site analysis and let's analyze this yield. This yield has I'm gonna show you a string observation. You can see it here, but sometimes we don't check, you know, when we have a lot of information, we don't check in very much detail, but we have, for example, strange data. So just for a minute, just omit this, that we have seen this. And let's assume that I'm gonna just analyze the trial omitting that information. Line, genotype, column, row, just to see what happened to the readability, just to see what happened to the residual, etc. Just one single point. So as you can see here, now my readability is 0.12. Residual is pretty high. The R-square coefficient of variation, and it's just one single point. We can think like, but it's only one observation, but look at this, it's making a huge damage. And I am going to take advantage of this just to show you this option that we have here, which is basically to remove outliers. So just by clicking these remove outliers, it's gonna appear this option here to remove. I can define, okay, I wanna check once, I'm gonna check twice or 3 times if there is something strange in the data. In this, I'm gonna say, please check if there is something strange, remove it, and then refeed the model. So the method we use is the one described in many books, which is basically under the assumption of the normal distribution. We know that the residuals, you know, they follow a normal distribution and they have a range, 3 and -3, in the scale way, in the scale way. So if there is something beyond the limits, so we can think about removing or omitting basically the data point. Now that we have removed that data point, look at this. Now we got a good editability, 0.65, residual standard error. Now we got everything like quite good. But just to make sure that we understand a little bit about the damage that can cause one single observation. I didn't show you. I'm gonna just leave it here, and I'm gonna jump to the residuals just to see the boundaries that we create when. Let me show you just 1 second. These ones. This is basically showing us the residuals against an index, just the values, and we can see if there is something strange, where it's located. And here in the QQ plot, we can see, and this is gonna tell me what is the observation. So here is, look at this, is because probably someone made a mistake by typing yield and it moved the point a little bit. So probably that's something that can happen, But we have to make sure that we remove the observation and then we redo the analysis and etc. etc. When it comes to, many trades, I can also analyze it here. We are just in single trials analysis. So this is gonna run trade by trade. I have yield, days to flowering, DPN, days physiological to maturity. For example, 100 seed weight. I complete just the fields that I need, call, row. There are some of them that are not mandatory, but call and row for sure are gonna be mandatory because it's basically the approach I am using here, spots. Internally, MrBean is gonna start by fitting the first trade, the first one, then the second trade you have there, and so on. At the end, it's gonna save the variance components, the blabs, the blues, depending on what you have selected. And you are gonna be able to see, these plots for all of the trades you have fitted. So this is days to flowering, BPM, 100 seed way. And you can also see this, like this button here can show you the percentage. I mean, how much is the spatial variation. And if you want to download this plot, you can also do it by clicking this button here, yellow button here. And you can also define the width and the height. And this is Pearson correlation between the trades. On the diagonal, we will see the readabilities. Here is the ranking plot. And we can more or less to see or to run a principal component analysis because we have multiple trades. So it is basically a table where we have the genotypes as individuals and the traits as a variables. And we can basically end up with this kind of analysis for selecting for multiple traits, for instance. We can also check a dendrogram if we want, and also download the plot if we interested in. Yeah, as I said, we are able to see the variance components, and if we have fitted, if we have taken the genotype as random, we are gonna be able to see the habitability on this table, outliers, it's gonna says, okay, you have this strange observation, you have two, etc., etc. And also it will give you the predicted values, by each trade, by each line, and their standard error. We can download this table in a long format and also split the table just to the right to see the trades one by one on the right side in our Excel file. And also, if we detect something, I mean, if MrBean detects something strange in the data, I mean, a strange observation, is gonna show you all of them in this table by trait. Days to flowering, this is basically where it's located, the call tree, the row this is the fitted value and the response, and so on. I see some questions in the chat, or let me check. Yeah, this is, I mean, when it comes to multiple sites, I can also jump to this model here. And also, I have many data during many years, and I want to analyze it all together. Remember that this module, you will need to have the row column information for all of them. And MrBean is gonna run one by one. So this trial, in 2021, this trial in 2022, this new trial in 2023, and so on. And
We have a question in the chat.
yeah,
I don't know if you want to answer it now. Somebody's asking if it is possible to have those software online.
Yeah, for sure. We are able to run it offline because they are basically running on your local computer. So this is open on the browser, but it's not because it's taking services from the network. No, it's just because it's the way, for example, Shiny, or we put the app, But yeah, for sure, if you don't have internet access, you are gonna be able to play with the app. That makes me think about something, which is that we can also create icons. This is for Windows users. We are gonna be able to create an icon. For example, if someone doesn't want to open R and then copy that line of code and then open this in the browser. So just by clicking on these icons, you are gonna be able to see the app on the browser again, but without worrying about opening R Studio, etc., etc. But for sure, you will need to have installed R and R Studio, for example, in your computer. That is gonna run in the backend. Let me check.
And we will be having shortly some of these tutorials also in our YouTube channel. So you can see how to download R and R Studio as well. There is an installation video in there.
That's a good point, exactly. And also, if someone is more familiar with Docker, we are also using Docker to put our apps there. So if you are more familiar with this, you can also download the Docker app. Oh, let me check if I haven't logged in here. Let me check if I have it, MrBean app. We can search here, MrBean or FielDHub. Let me check. FielDHub. Exactly this one. So the way we have to basically to download this by using Docker is basically to pull this repo. We can find this one, FielDHub, and you are gonna be able to find also MrBean. If you are more familiar with Docker, so you can also download from here. Yeah, I don't know if there are more questions. If there is something I didn't cover. Anna?
Right now, I think that we are okay. I just wanted to mention that, this application it has been very much used by many of our breeding programs here at NDSU. And this has helped us to easily, for our breeders, or even some of our agronomy teams have been using it as well to make quickly decisions. So if you have any questions on how to utilize it, please let us know now. We are showing you pretty much the single location analysis. And one thing that it's important to mention is usually when we do the analysis, let's say for a single location, we consider the genotypes not to be random, but we consider them facts. And then when we do the analysis across locations, then that's when we consider the genotype random.
Excellent. That's a good point. When it comes to multi-environmental trial analysis, the approach we have available on MrBean is the one that is mentioning Anna, which is the two-stage approach. In the first stage, we feed the genotype as fixed. We use the standard errors as a weights with some math there. And then in the second stage, we use the blues, and then we add the weights, you know. But we will see that in the next one. This is just to conclude, to close a little bit, some of the developments, MrBean, FielDHub, and also contributions to QBMS, which is the app that is basically querying the information from the databases. And this one is probably, I will show you this one in the future, just to mention it. And yeah, thank you so much. I think that's all from my side. If there is any questions.
Perfect. Thank you very much, Johan and Didier. And then this will be the end of our training for today. Thank you very much.
Thank you.
Lance.
Thank you. This was a